So let me start. So today I'm going to talk about reinforcement learning with robustness and safety guarantees. Okay. So I'm sure that all of you here are familiar with reinforcement learning at some level. Some of you may be doing your active research on reinforcement learning on RL theory, algorithms, or even application of RL into specific problems of interest. Reinforcement learning is a class of machine learning focusing on how to learn the optimal sequence of action in an unknown and evolving environment in order to maximize the cumulative long-term rewards. So this is the canonical diagram that we typically use to represent reinforcement learning paradigm. A learning algorithm interacts with an environment by taking a sequence of action. The learning algorithm gets the state observations and the reward. And the goal of the learning algorithm is to maximize the cumulative long-term reward. As an example, consider the problem of learning to play a Atari game. The actions can come from the joysticks. The environment is Atari game engine, and the screen images are the observations, and the rewards are the actual points in the game. In another example, the actions can come from the steering wheel to the environment of an autonomous vehicle, and the observations can be the camera or LiDAR images. Reinforcement learning had some shining successes in the past few years. In 2015, DeepMind published this impressive work of a deep RL algorithm that is able to outperform human agents in playing a Atari game. This was followed by a series of interesting deep RL algorithms from DeepMind, including the impressive AlphaGo algorithms and its variants, which were able to outperform human agents, actually human experts in much more complicated games such as Go, chess, and shogi. RL also had some interesting successes in the robotics domain. For example, this work from OpenAI in 2019 got much press coverage at that time, and they used an RL algorithm for a robotic hand to solve the Rubik's Cube problem. And there are other impressive newsworthy articles, including the chip placement design work from Google and the recommendation system work from Netflix and Microsoft. But if you carefully read the success stories, you will immediately realize that most of these RL success stories are limited to very structured or simulated environment, such as games or simple robotic setting. In fact, the success stories of reinforcement learning in real-world engineering systems are rather limited. So what is holding up reinforcement learning from emerging as the go-to solution for the control of real-world engineering systems? So I believe that one of the main reasons is the fragility of reinforcement learning algorithm, in the sense that this algorithm lacks robustness and safety guarantees. So anyone who has trained an RL algorithm must be familiar with scenarios like this. In the Mujoko's environment simulation here, a hopper is falling repeatedly during training and sometimes even during testing. It is natural to consider scenarios happening in the real world where a robot controlled by an RL algorithm falling down while executing its task. In fact, if you read the fine print, you will realize that this work, which got much press coverage at that time, was successful only 32% of the time. And of course, naively using any ML-RL algorithm without any safety or robustness guarantees can lead to catastrophic outcomes in the real-world engineering system, as we have seen in a series of bad examples recently. So how do we develop scalable reinforcement learning algorithms that are provably robust and safe? This is one of the fundamental questions at the core of my research effort in the past couple of years. And today I will try to present some of my recent research on addressing these fundamental questions. So first, I will talk about robust reinforcement learning. So first, I will talk about robust reinforcement learning. We actually have a series of work on the topic of robust reinforcement learning from our group. In today's talk, I will mainly focus on this particular work, which was presented in NeurIFS 2 months back. This is a joint work with my PhD students, Kishan and Sayan. Kishan is the lead author in this series of work. And for this particular work, we got this wonderful opportunity to collaborate with Dr. Muhammad Gawam Sadeh from Google Research. But before discussing my algorithm on robust reinforcement learning, let's ask ourselves, why do we need robust reinforcement learning? The key reason is the simulation to reality. Reinforcement learning algorithm typically learn a policy by training on a simulator. However, the real world system parameters can be different from that of a simulator. For example, in robotics, the mass, the friction, sensor noise, action delays, etc., can be different between the real world system and the simulator, which is trying to approximate the real world system. And it is known, both in theory and practice, that RL algorithms trained on a simulator may perform poorly in the real world system due to this simulation to reality gap. And this is not a hypothetical question. This is actually a And this is not a hypothetical question. This is actually a serious problem that is being actively addressed both by the academia as well as the industry. You will find a number of papers, seminars, workshops on addressing this problem from academia, as well as some interesting recent efforts from the industry on addressing this problem. In fact, it is recognized as one of the most important challenges that we need to overcome to make RL algorithm deployable in the real world engineering systems. So in this context, I address the following problem. How do we develop scalable reinforcement learning algorithms that are provably robust against parameter mismatches between the simulator model and the real world model? So as standard in RL, I use the formalism of Markov decision process to model this problem. I'm assuming that all of you are familiar with MDP somewhat. So I'll be very brief here, not to bore you with the notation. So in an MDP, we have a set of states, a set of action, a probability transition function P. So P of S prime given S comma A represent the probability of moving from state S to S prime if action A is taken. The P is also called the model of the system. So for the rest of the talk, I will use the keyword model instead of probability transition function. There is a reward function associated with each state action pair, and a control policy is a mapping from the state space to the probability distribution over the action space. An MTP is a very useful and a general formalism that can capture most of the real-world control problem of interest. For example, in this robotics control problem, the position of the robot can be the state, the action can be the force or torque that we apply to move the robot, and the reward can depend on the posture or the gait of the robot. And at any given time t, a control policy phi selects an action AT given the current state ST, and the next state ST plus 1 will be realized according to the model of the robot. The value of a policy is the expected cumulative discounted reward that we can get by following that policy. And the optimal value function is the maximum value a policy can achieve. And the optimal policy is the policy which achieves that maximum value. And the MDP question is the following. How do we find the optimal policy when the model is known? And we know that dynamic programming provides an answer to this question. For example, you can use value iteration or policy iteration for finding the optimal policy. Reinforcement learning is the learning version of this MDP problem. That is, how do we learn the optimal policy when the model is unknown? So in this part of the talk, and I will focus mainly on the offline reinforcement learning problem and offline robust reinforcement learning problem. Here also, the goal is the same. How do we learn the optimal policy when the model is unknown, but using only historical offline data without having access to any direct interaction with the environment or with a sophisticated simulator model? So offline RL is a very promising paradigm for many real-world applications, such as autonomous vehicle recommendation system, power system, clinical treatment, etc., where it's typically easy to get historical data, but it is very difficult to model the whole system and expensive or even unsafe to have direct interaction with the real-world system. For example, in power system, you may be able to get operational data, but definitely not advisable to have real-world interaction with the power system for the learning purpose. So whenever we say learning in the context of machine learning, it means that there is some data to learn from. Where does the data come from in reinforcement learning context? In the offline RL, as I just mentioned, we assume that the learning algorithm has access to a set of data generated according to a behavioral policy from a nominal model. So our offline data is represented by script D, which is the tuple state, action, reward, and the next state. And the next state is generated according to this model. And most offline RL algorithms learn the optimal policy by explicitly or even implicitly learning about the underlying model. But what if the model is wrong? In this particular context, what if the nominal model which generated the data is different from the real world model on which you want to deploy the system? As I mentioned before, the simulation to reality gap is a fundamental challenge and arguably one of the most important challenges that we need to overcome to make our RL algorithm deployable in the real world setting. So I use the formalism of robust Markov decision process and robust RL to solve this problem. A robust MDP is similar to a standard MDP in the sense that it has the same state space, action space, and the reward function. Excuse me. But it is different because we consider a set of model instead of a single nominal model. So the set of model is script set of model we denote as script P is also called the uncertainty set. So the uncertainty set is defined as a Cartesian product of the uncertainty sets corresponding to each state action pair, script PSA. Now the uncertainty set corresponding to a given state action pair can be thought as a ball of radius rho around the nominal probability distribution with respect to that particular state action pair. So that rho is the radius of uncertainty and the D is a distance metric between two probability distributions such as PV, chi-square or here. Now the robust MDP objective is the following. Given the uncertainty set, how do we find the optimal robust policy as a solution of this optimization problem? So you want to find the optimal robust policy, argmax over pi, min over all possible models in the uncertainty set, and expectation of the expected discounted cumulative reward, where the expectation is taken with respect to that particular model from the uncertainty set. So intuitively, we want to find a max-min policy. Another way to think about it is by defining the robust value function. So I can define the robust value function V pi as min over P and V pi P. So essentially the value of a policy corresponding to the worst possible model. And our goal here in the robust MDP is to find the policy which will maximize the robust value function. So there is a one-to-one correspondence between the standard MDP objective and robust MDP objective. In the standard MDP objective, you want to find a policy that maximizes the value function. Here, you want to find a policy that maximizes the robust value function. Any questions? Now, robust RL problem is the learning version of the robust MDP problem. That is, how do we learn the optimal robust policy when the uncertainty set is unknown? So where does the data come from in the robust RL problem? Here in the offline robust RL context, we make the same standard data assumption that we use in the non-robust RL context. That is, we are going to assume that the algorithm has access to the offline data generated according to behavioral policy from a nominal simulator model. So my data, offline data is script B, which is the tuple state, action, reward, and the next state. The next state is generated according to the nominal model P naught. So I emphasize that's a nominal model P naught, which may be different from the real world model P. So this immediately brings out one of the many challenges in robust RL. So if you look at this equation, to compute the optimal robust policy, you may have to evaluate this expectation with respect to all the possible models in the uncertainty set, but you have the data only from the nominal model. Clearly, you cannot generate the data according to each and every models in the uncertainty set. You have to leave with the data that you have. So how do we solve this problem? That is one of the challenges that we need to overcome. So before I describe the solution approach, let me quickly summarize the related work in the slide. So the robust MDP formulation was first proposed and developed in two seminal parallel work by Gerud Iyengar and Dileep Kalathil, one from Berkeley and one from Stanford. And there was a series of work on studying robust MDP, but most of this work was on the series of work was on planning problem, but not on the learning problem. Of course, RL community addressed this problem from the learning context, but as standard in the literature, the initial works were mostly on the tabular setting on linear function approximation setting, which may not scale to large state space. There are obviously deep RL algorithms which is trying to solve this robust MDP problem, but as standard in the deep RL literature, most of these algorithms are based on heuristics without provable guarantees. I acknowledge that this is only a partial list. Robust learning is a very broad area. Here I included only the works which essentially use the robust MDP formulation. For example, in another stream of work, there is robust control literature, which is studying this problem, but I just focused on this here. Apologies if I'm missing anything important. So in this context, our main contribution is the following. We address the offline robust RL problem with very large state space using function approximation with provable guarantees on the performance of the learned policy.
Quick question.
Yes.
Regarding, if you go back to the previous slide, please, regarding the learning problem in robust MDP, can you give us an idea of how the solutions look like? Regarding the planning problem only, not with data.
Thank you. That is indeed what I'm going to talk about in this particular slide. Okay.
Okay, thanks.
So before discussing the learning problem, let's first understand how do we solve the planning problem, right? So how do we find the optimal robust policy if the uncertainty set is known? This can be done by robust dynamic programming. In fact, we can actually define a robust Bellman operator T, which is a robust version of the standard Bellman operator. So the robust Bellman operator operating on Q can be defined the following way: R plus gamma times in for all possible models in the uncertainty set and an expectation with respect to that particular model. So you can realize that if there is no in here, this is the standard Bellman operator. So this is when with the in for all possible model, this is the robust Bellman operator. But we can show that many of the useful properties of the Bellman operator carry over to the robust Bellman operator. In particular, we can show that T is a contraction operator, and so there is a unique fixed point. So we can actually define the robust Q iteration. I can define Qk plus 1. Excuse me. I can define Qk plus 1 as Tqk, and since T is contraction, Qk will converge to Q star. And the optimal robust policy can be computed as the argmax policy. So this is how we solve the robust dynamic programming. But our goal is the learning problem. So how do we solve the robust RL problem using offline data for RMDPs with very large state space? And I propose an algorithm called robust fitted Q iteration algorithm to solve this problem. Okay. So the basic idea behind our robust fitted Q iteration algorithm is straightforward. I want to approximate the exact RQI update with function approximation using offline data. So I want to get the next iterate Qk plus 1 as a solution of an optimization problem or a function class script f. Script f is the class that I'm considering for representing the robust Q value function. Intuitively, I'm trying to get the best fit for Tqk by minimizing the squared error. While this might seem simple, straightforward, it is particularly challenging in the robust RL context, mainly because evaluating robust Bellman operator with function approximation using offline data is challenging. To see one of the challenges, let's recall the robust Bellman operator. As I mentioned before, there is an inf over all possible models here. So solving that inf problem itself is difficult, and there is an expectation. So estimating that expectation using the data only from the nominal model is also very challenging. So in our work, we propose to overcome this particular challenge by a dual reformulation of the robust Bellman operator. So let me state that in the form of a proposition. So let's consider an RMDP with uncertainty sets with P. So here I'm going to restrict the distance measure to only total variation distance for defining the uncertainty set. Then the robust Bellman operator can be equivalently written in the following form. So there's a lot of notation. Let me unpack that for you. There are two takeaway messages here. The first thing that you can notice that the expectation over all possible model is now replaced with respect to expectation over only the nominal model P0. The objective is different, but even though the objective is different, since the expectation is only with respect to the nominal model, you may be able to estimate that using the offline data. The second thing to notice is that the infimum or the minimization over all possible model is now replaced by a scalar minimization over eta. And then we can show that inner optimization problem is convex in eta. So this kind of dual reformulation techniques is known in the distributional robust optimization literature. We essentially borrow that idea and apply that in the context of robust dynamic programming. But this formulation alone will not solve our issue, because here, if you write it in the dual reformulation, you have an inner optimization problem to solve. So let me rewrite this inner optimization problem in the next slide. It looks like this. So you can see that there's an expectation outside, there's an infimum inside. So that still requires solving an optimization for each state action pair, which is clearly infeasible for large MDP. So here also we have a simple, straightforward idea to overcome this. So we want to reformulate this problem as a functional optimization problem instead of solving it as a multiple scalar optimization problem. So for that, I'm going to define a dual loss function. So L dual, the dual loss function for the function G for a given Q function is defined in the following way. Here also there is a lot of notation, but one quick thing to notice here is that equation 1 and equation 2, the objective in the black font are identical, except that this eta in equation 1 is replaced by G evaluated at S and A. Otherwise, they are identical. But they are different because in equation 1, there is a scalar infimum for each state action pair, and the infimum is inside the expectation. Here, the infimum is outside the expectation, but that's a functional infimum, functional optimization problem, or an appropriate function space. Okay. Now, can I solve the equation 2 instead of equation 1? Because we are exchanging expectation and minimization with appropriate function class. For example, if your function class is rich enough, you can show that you can do that even if the state space is continuous. So you can interchange the expectation and minimization. So instead of solving the multiple scalar optimization problem in equation 1, I'm going to solve equation 2 or a functional optimization problem. So for any given Q, I can solve this L dual function over the appropriate function class to get the appropriate dual function. Due to time constraint, I will skip over the other details of RFQA algorithm. I'll just jump to the algorithm. So in RFQA algorithm, I start with an offline data set, and I have two function class scriptf. Scriptf is a function class that I use to represent the robust Q value function. Script G is the function class that I'm going to represent using to represent the dual variable function. RFQA algorithm operates in iterate. In the first step of each iterate, I perform the dual variable function optimization for a given Q iterate Qk. So we compute the dual variable function corresponding to Qk by solving the same optimization problem that I described before. But that optimization problem was with respect to the true expectation. We don't have true expectation, but we have the data, offline data. So you can use the offline data to estimate that function. So, and we can use the empirical risk minimization approach to solve that problem. This will indeed introduce some error, but we can get an upper bound for that error. Okay. So what will we do? So given a Qk, I get the dual variable function for that Qk. Now, given the dual variable function, I get the next iterate Qk plus 1 by solving the least square problem, which I presented earlier. Okay. Now, this is the exact equation for that least square problem. Again, least square problem requires like an exact expectation. We don't have the exact expectation, but we can again use the offline data to get an empirical estimate about this least square problem. Here also, there will be some error. We can appropriately bound that error. And this continues for capital K number of iterations. Yes.
So what's the complexity for like step 4 and step 5?
Pardon?
What's the computational complexity for step 4 and step 5?
So here we don't exactly calculate the computational complexity because we are considering a very large state space. So we are just treating it as an empirical risk minimization problem. So my goal is to characterize the sample complexity and computational complexity. Okay, so now we have an algorithm. What is a performance guarantee? I can show the performance guarantee under some standard assumption. So I'm not going to explain this assumption in detail. I'm just going to mention that these are the standard assumptions that you will see in non-robust offline RL literature also. So essentially using the same assumption that we use in the non-robust offline RL literature, we can give the performance guarantee for the robust RL. Okay? So the first assumption, constant reliability, essentially imply that the offline data has some coverage. That's a standard assumption in the non-robust offline RL literature. Approximate completeness roughly means that the function class that you use to represent the Q value function is rich enough. And in this particular case, I propose the natural extension of assumption 2. Essentially, I'm assuming that the function class that I'm going to using to represent the dual variable function is also rich enough. So using the same standard assumption as in the non-robust offline RL literature, I can give the following performance guarantee. So let pi k be the output of our RFQ algorithm. Then I can get the following bound. The robust value of the optimal robust policy minus the robust value of the output pi k can be upper bounded by these two terms. So let's look at the second term. There's an epsilon C and epsilon dual that is coming from approximate completeness and approximate dual realizability. So if it is small enough, so you can neglect that term. There's actually a gamma power k, So if you have K large enough, the number of iteration is large enough, again, you can neglect the second term. So the first term is the important term. And you can see that that is of the order of 1 over square root n and log cardinality of the function class. Okay. So this is a standard statistical learning bound that you get in many machine learning result, including in the non-robust offline RL. So essentially what I'm trying to emphasize is that using the same standard assumption as in the non-robust offline RL, we can give a performance guarantee for the robust RL algorithm. Okay, so now we have a theoretical performance guarantee, but is it good? Does it work in practice? Right? So we did extensive evaluation in Mujoko environment. So I'm going to show the Mujoko evaluation.
Excuse me for interrupting. I have a question in your previous result, please.
Yes.
It seems that the left-hand side is an expectation over the initial state. Does the right-hand side have any dependence on D0?
So that dependence is kind of captured in the concentrability, which I'm C.
Got it. Yes, I see. Thank you.
Yes.
So yeah, that's a question. I guess in the like a standard of learning, like and just look at 0 and then in the denominator is 1 minus gamma square. But here's
No, I think it is cube.
it's cube.
Yeah.
Okay. Yeah.
So square. I think it's. I'm pretty sure that's cube, but let's chat after that. Thank you. I don't know about the recent result that's in the last half a year or so, but when we were referring, it was cube. Sorry. Okay, so coming back, what is the performance? How does it work in practice? How does it work in simulation? So here I'm going to show you the performance evaluation in the Hopper simulation environment. In this plot, I'm evaluating two algorithms. The red line is the FQI algorithm, the standard non-robust algorithm, fitted Q iteration algorithm. The black curve is our algorithm, the robust version of that standard FQI algorithm. Y-axis is the average cumulative reward in 20 trials. That's kind of performance evaluation. X-axis is where I'm introducing the simulation to reality gap. So by changing this parameter, joint friction loss in the Hopper environment, the value 0 means that there is no simulation to reality gap. And as I increase X value, there is more and more simulation to reality gap. So the testing environment and training environment differ more and more. As you can see, when there is no simulation to reality gap, the performance are similar. But when we introduce simulation to reality gap, the performance of the non-robust FQA algorithm is falling quite sharp, fast. But the performance of our robust FQA algorithm, RFQ algorithm, remains more or less the same, okay, as intended. That's the idea of robustness. We did this evaluation in a number of other environments. We also compared with the TD3 algorithm, like a state-of-the-art policy gradient algorithm. I think the performance will be better appreciated in the simulation video. Okay, so here in the first video is the performance of TD3 algorithm on the nominal model. So as expected, it is performing well. There is no simulation to reality gap. The second video shows the TD3 performance when we introduce some simulation to reality gap by changing the control actuator range. As you can see, when there is simulation to reality gap, the standard policy gradient algorithm is failing. But the third video is essentially our algorithm in the presence of the same simulation to reality gap, and you can see that that is working. And we essentially compared this with other algorithm, for example, FQA algorithm, same story. The first video, the standard non-robust algorithm with no simulation to reality gap working. Second video, when we introduce the simulation to reality gap, standard algorithm fails. Our algorithm will work in the presence of simulation to reality gap. For fun, we actually tried this by changing the gravity by 20%. So you can see the first video is FQA algorithm. It is not able to work, not able to hope in the reduced gravity environment. Second is TD3 algorithm is trying to hope in that reduced gravity environment. Our algorithm, you can see that it is working, and you can see the reduced effect of gravity in that kind of moonwalk kind of jumps. Yes.
Each time the same quantity which is applied, or
Yeah, so the robust policy means that like there is no real-time adaptation. I have just one policy and that is being applied.
We have to train one policy when we change the gravity, when we have to change the friction, or
So this we changed one policy. This we applied one policy. Okay, so very quickly I will quickly talk about this recent work where I got this great opportunity to work on a real-world application and demonstration of a robust RL algorithm. This is a joint work with Professor Mobile Benedict from the Aerospace Engineering Department at Texas A&M University. Also with two brilliant students, Vishnu was a master's student in my department, and Bochan was a PhD student in the Aerospace Engineering Department. So Professor Mobile Benedict is an aerospace engineer. He builds things and fly things like drone and helicopters. He's a real engineer, unlike me. I prefer more theorems, proof, and algorithm. He builds things and fly things. So for him, an upper bound does not characterize as a valid proof of an algorithm, even if it matches with the lower bound. For him, an upper bound works when he's able to, or a theorem for an algorithm works when he's able to use that algorithm in his application and make drones fly. So some couple of years back, he told, I think around 2 years back, 1.5 years back, he told me that he's working on an algorithm. He wants to develop an algorithm for autonomous ship landing for vertical takeoff and landing capable UAVs using only a monocular camera in the UAV for tracking and localization. He told me that this is a very challenging problem because of the small landing space, 6 degrees of freedom ship deck motion, limited visual reference for localization, and adversarial wind gust. And he tried some standard algorithms like PID controller or like modified LQR, which did not really work. So we were discussing this problem, and I asked him, can we use robust RL to solve this problem? And he said, yes, let's try. And that was the beginning of this project. This started before I started working on the RFQ algorithm. So at that time, we used a different robustness criteria and different algorithmic approach to solve this problem. So as I mentioned, RMDP solves a max-min problem, which can be conservative in some scenarios. So at that time, we used a relaxed robustness criteria. So in particular, we use this soft robust objective where the min overall possible model is replaced by expectation overall possible model, a softer objective. So this objective is known in the robotics plus RL literature also, which is called domain randomization. I think many of you may be familiar with domain randomization. To those who are not, the domain randomization is a simple idea. Essentially, the idea is to randomize the simulation model parameters during training. So the policy or the neural network, which represents the policy, will be exposed to a wide range of environments at training. And this policy trained in the simulation will generalize to real world with no additional training. Okay. So essentially, it's an intuitive or heuristic approach to overcome the simulation to reality gap. So we decided to follow this approach, and we developed a soft robust RL algorithm using only simulated training, considering many robustification. And then we tested it on the real world setting without any additional fine tuning. The students actually built this platform. This is like a model of a ship deck platform. The green bar is the horizon bar, which we used to localize the drone. We used a big fan to kind of create the wind. I think rather than telling you how it worked, it will be better I show the video. For those who are in the Zoom, are you able to see the full screen or the partial screen? Okay, great. Okay, so this is the base scenario. You can see the movement of the platform. This is a simple PID controller when there is no winch, and it is working well. Then we created this diagonal wind gust. You can see a big fan, the effect of wind in this polythene cover. And it's trying to, the PID controller is trying to land, but it's not working. And our robust RL control algorithm is able to fight off that wind. And then land on the platform. So the effect is a little more dramatic when I have this orthogonal wind gust. you see that standard PID control algorithm is not able to control the drone, and it's kind of got flown away. And the soft robust RL algorithm that we developed was able to fight off that wind. You can see that effect of like, it's not very smooth, but it's fighting off the wind inch by inch, but not losing the control and going and landing in that platform. Yes.
Do you use the same policy for different direction of the wind?
Yeah, same robust policy.
Did you train this without wind?
So this robust, so soft, so as I mentioned, this is a soft robust criteria. So we randomize the environment. So during the training, we tried winds. Don't remember exactly. So we tried by, yeah, don't exactly remember, maybe 1 to 4 per second or something.
In a simulation.
In a simulator, yeah. So everything is done on the simulator, and then this is tested in the real world without any additional fine tuning. Okay, so in the remaining time, so give me a 5 minutes warning when it's ready. Okay, so great. So in the remaining time, I will quickly tell about my work on safe reinforcement learning. We actually have a series of work on the topic of safe reinforcement learning. Today, I will focus mainly on this first paper, which was presented in NeurIPS 2 months back. So for this multiple papers, I got the wonderful opportunity to collaborate with many PhD students and my colleagues in the ECE department at Texas A&M University. Archana, Arya, Rohida, Tao, and Sapna are the PhD students, and Srinivas, JF, Kumar, and Chao are the professors in the ECE department. So just like I asked the question, I asked this question myself when I was working on robust RL. Why do I need to work on robust RL? What is the motivation for robust RL? In the same way, why do we need safe reinforcement learning? But I think here maybe it may be a little more intuitive, because the control policies for any real-world engineering system should maintain some necessary safety criteria to avoid undesirable outcome. We want to avoid collision in autonomous vehicle. We want the robot to fall down. Don't want the robot to fall down. We want to avoid blackouts in power systems. But reinforcement learning algorithm may violate the necessary safety constraints during learning and during deployment. And the safety constraint violation may lead to catastrophic outcome in real-world engineering systems. So how do we develop reinforcement learning algorithm that find the optimal policy without violating the safety constraints during learning and during deployment? This is the question that I have tried to address in a number of works. So just like I used robust MDP formulation to address that intuitive problem, here I'm going to use the formalism of constraint markov decision process. This is a standard formalism now used in the literature to model safe reinforcement learning problem. Here we model the safety requirements as constraints on the cumulative cost. So in a CMDP, there is a same state space, action space, and the horizon H. So here I'm going to consider like an episodic CMDP, not the infinite horizon discounted reward I'm considering, because I want to characterize the safety during learning. Different from the standard MDP, a CMDP has two reward function or cost function. Here we have an objective reward function R and a constraint cost function C and a safety constraint C bar. So the value function, value of a policy phi for a reward function or cost function can be defined in the following way. That is nothing but the expected cumulative cost or expected cumulative reward. So in CMDP, unlike the standard MDP, we have two value functions, an objective value function with respect to the objective reward function R, and a constraint value function with respect to the constraint cost function C. And the CMDP problem is to find the optimal safe policy pi star, which maximizes the objective value function such that the constraint value function is less than or equal to C bar. Okay. So safe reinforcement learning or constraint reinforcement learning problem is a learning version of the CMDP problem. Here our goal is to learn the optimal safe policy when the model is unknown, but without violating the safety constraints during learning. So to bring out this idea, I focus on an episodic online learning setting. That is, the algorithm select a learning policy in each learning episode. It's a finite horizon problem. So in each learning episode K, the algorithm selects a policy pi k. Then the pi k is used to collect the data, that is state, action, reward, and the next state the data. And the algorithm uses the data to update the policy. The goal is to converge to the optimal safe policy. But in safe reinforcement learning, we have the additional requirement that each of this policy in the sequence should satisfy the safety constraint. So the constraint value function for the policy pi k should be less than or equal to C bar for all k. So those who are familiar with the exploration exploitation ideas, you can immediately see that this online learning problem now is closely connected with the exploration exploitation problem in RL. But here you have an additional constraint that during exploration, the policy should not violate the constraints. Okay? So to bring out that idea, I defined two regret notions in safe reinforcement learning. Here, we have the objective regret, which is similar to the standard regret. So inside the summation, this is the difference between the objective value function corresponding to pi star and the objective value function corresponding to the learning policy pi k in the episode k. Constraint regret is nothing but the cumulative constraint violation. And our goal is the following. Can we develop a learning algorithm which will minimize the objective regret while keeping the constraint regret to 0? Excuse me. So let me quickly summarize the related work in the context of CMDP and constraint bandits in this slide. So there has been some very interesting works on exploration in constraint bandits. How do you learn kind of an optimal arm or optimal linear bandit problem, solve a linear bandit problem, given that you have constraint and you don't want to violate the constraint violation from Amani et al., Gasili Bita, Fraciano et al., and from Professor Laying's group here. And in fact, we actually used one of that proof idea from this paper to solve like a CMDP problem in one of our recent work. So in the safe reinforcement learning in RL can be divided, the works in safe reinforcement learning can be divided into two categories. There's a number of work which is trying to learn the optimal safe policy, but they allow constraint violation during the learning. So this bullet point essentially shows some of the works in that domain, including some works from my group. The other classes where I am focusing were exploration in constraint RL without violating the safety constraints. I would like to emphasize that again here, Professor Laying's group has a almost concurrent work with our the second work that we have here, which I am presenting here. Their algorithm is called triple Q. So I'm sure the students are here or watching Zoom. So again, I'm assuming acknowledge that this is only a partial list. Here also I'm focusing on CMDP formulation. Safe RL is a broad area. There may be other formulation. Apologies if I'm missing anything important. Okay, so classical regret minimization algorithm in bandits and RL follow this idea of optimism in the face of uncertainty. So for the first thing that we asked ourselves is, can we use OFU algorithm to solve the safe reinforcement learning problem? So what is OFU algorithm? OFU algorithm is essentially, you can formulate it as a model-based episodic learning algorithm. So in each learning episode, we estimate the model P hat K, and we construct an uncertainty set script PK around the estimate P hat K. So here beta is the radius of the uncertainty set. That's of the order of 1 over square root of NK of SA. So NK of SA is the number of times the algorithm has seen samples from the state action pair SA until the episode small k. The exact form of the radius is not important because that's to apply the Bunchian inequality. But important thing is that it's of the order of 1 over square root of NK. Then in the OFU approaches, we find the policy by solving this optimization problem. So here we select an optimistic model from the uncertainty set, and we find the optimal policy for that optimistic model. So PK is the optimistic model, and pi k is the optimal policy for that optimistic model. And this repeats. And in most standard bandits and RL algorithm, a variant of this approach will give you like an optimal solution, which will minimize the regret. But intuitively itself, it's kind of intuitive that this naive OFU approach may not solve our safe reinforcement learning problem. Why? Because we are being optimistic with respect to the model. We are not considering the constraint at all. So being optimistic with respect to the model may violate the constraint. Okay? And in fact, this was shown in another work where they showed that the naive OFU style algorithm will get you the order of square root k objective regret, which is good because that's order optimal regret for the objective regret. But the constraint violation regret will also be order of square root k, which is bad, which essentially means that you are keeping on violating the constraints. So our question was the following: can we get an order of square root k objective regret while achieving zero constraint regret? So how do we solve this problem? So we asked ourselves, why is the naive OFU algorithm is failing? As I just mentioned, it is because it is optimistic with respect to the model. It's not only optimistic with respect to the model, it is not considering the constraint at all. So it is optimistic with respect to the constraint also. Then we had a simple solution to overcome this. Hey, it is violating the constraint because it is optimistic with respect to the constraint. So let's be pessimistic with respect to the constraint. Okay? So we thought that, okay, if we avoid the constraint violation by being pessimistic with respect to the constraint, can we solve this problem? So we did that by considering a pessimistic cost function, C bar. So C bar is C, the standard cost function, plus a pessimistic term. So you can see that the pessimistic term is proportional to the beta, the radius of the uncertainty set. Will this approach work? It will work in one way, that is, it will work and it will not violate the constraint, but it will not work because your objective regret will be very bad. That is, if you use this approach in the OFU, if you use the pessimistic cost function in the OFU, you may not violate the constraint, but you won't get any reasonable performance. So it's very pessimistic. So we have a pessimistic solution, but it's very pessimistic. So how do we overcome this problem? So we thought that, okay, we are being very pessimistic. Let's introduce some more optimism. So we achieved that by the double optimism with respect to the reward function. So we created an optimistic reward function R bar, which is a standard reward function plus an optimism term. You can see that the optimism is also proportional to the radius of uncertainty set, but with a different constant. Then by combining this, we proposed our algorithm. So our algorithm looks similar to the OFU approach, but it is different in the following way. Instead of the standard reward function, we have an optimistic reward function. Instead of the standard cost function, we have a pessimistic cost function. And in addition, we have the standard optimism with respect to the model. So we have two optimism, one optimism with respect to the model and another optimism with respect to the reward and pessimism with respect to the cost function. So we called our algorithm, a little bit cheekily, doubly optimistic pessimistic exploration algorithm DOP. And the solution is that solve this problem at each learning episode and then use that learning algorithm in that learning episode. So one thing very clear before starting this problem itself is that intuitively, it is not possible to guarantee safety in the beginning of the learning if you do not know anything about the model. Okay? So one standard assumption used in the literature is that you assume that there is, a safe baseline policy. That's not the optimal policy, but a safe baseline policy. And you can start with a safe baseline policy. So we use the same approach. Our algorithm uses a safe baseline policy for the first K0 episode. That K0 does not depend on the total number of episodes, capital K. It's a constant. We can give a precise characterization of the constant. And our algorithm is the following. First K0 episode, use a safe baseline policy, then use the DOP policy. So we can show that this algorithm achieves the desired results. Excuse me. So under the DOP algorithm, of course, with high probability only, we can achieve zero constraint regret. That is, the learning policies selected by the algorithm do not violate the constraints during that learning. And at the same time, you get almost optimal regret, almost optimal because it is of the order of square root K. And I believe it's order optimal with respect to action. I think you can save a little bit on the state and horizon. That's why it's almost optimal.
That depends on delta.
So the delta is 1 over delta. That C bar by C bar B is the delta that automatic. Okay. So in fact, this DOP algorithm is actually an improvement on a previous work from our group, where we kind of saved some regret factor. Also, it performs much better in the simulation performance. Okay. So I'm not going to spend time on the simulation performance here due to time constraint. Now, DOP gives provable guarantees, but as you have seen, it's like a tabular model-based episodic learning algorithm, but it does not really scale to large state space. Now, the question is that can we develop scalable reinforcement learning, safe reinforcement learning algorithm with provable guarantees? In other words, can we develop, in our context, can we develop policy gradient algorithm for constrained Markov decision process? So from our group, we actually have a work on fast converging policy gradient algorithm for CMDP, which is in the archive. Then we realized that actually that methodology can be used to solve a class of problem, more generally characterize multi-objective reinforcement learning. Why it is multi-objective? For example, CMDP can be thought as multi-objective. You are maximizing one objective such that the other objective is less than or as a constraint. You can actually think of a nonlinear combination of multiple objectives. For example, if you want to ensure some kind of alpha fairness, log utility fairness, so you can think about like a log sum of the value function. And for those problems, there's no dynamic programming approach. So you need to use optimization approach. So can we solve that class of problem by policy gradient? A recent work from us in the new RIPS essentially solved that problem. And then CMDP will become a special case of that. And we can show that we can get a global convergence rate of the order of 1/t. Okay, so to summarize, so I presented some part of the work from our group on robust RL and safe RL today. So as I mentioned, why I wanted to work on this work was that I believe that simulation to reality gap is a very important problem that we need to solve to make RL algorithm deployable in the real world engineering system. And in addition to the simulation to reality gap, which is essentially considering the model mismatch, safety is another important factor that we need to consider. Okay? So, and again, since I am more on the theoretical and algorithmic side, I would like to formulate this from this mathematical methods and try to get provable guarantees for large state space problem. So for the robust RL, I use the framework of robust MDP and robust RL to solve this for large state space. For for the safe RL problem, I use the formalism of CMDP, solve this problem. And we have like a lot of interesting future possible directions here. We are currently developing some policy gradient algorithm for robust RL. I'm also generally very much interested in more fundamental questions like how do you develop stochastic approximation algorithms like TD learning, Q learning for robust RL algorithm for given the uncertainty set. And then I am interested in the robust and meta RL algorithm. So as you know, meta RL idea, essentially meta learning idea, indicates the ability to adapt in the real world. Robust isn't, and why do you want to adapt the real world? To overcome the simulation to reality gap. Robustness is also overcoming the simulation to reality gap, but being robust or pessimistic. So it is too extreme, right? So is there a sweet spot between that? You may not be able to completely adapt in the real world. There is some pre-training is required, and then you might want to start conservatively. So where is the sweet spot? How do you combine this robust approach and meta RL approach to come up with a better algorithm? So that is something that we are working on now. So with that, I will conclude. Thank you so much for listening, and I'll be happy to take any questions.
So maybe let's first let the audience on the group to ask questions.
Yeah.
Yeah, it's not like anyone have any questions to ask.
Can you go to the slide more maybe on robust RL?